Alright, hey guys, what's going on? So today we're going to be talking about renormalization coupling. So before we get into this, renormalization coupling is a very important topic when it comes to understanding exactly what is going on within that black box we've been talking about. So we have these Feynman diagrams. The black box is this space in which the two incoming particles will interact somehow. And what we talked about in the last video is that the only real condition that we need or that we observe in the natural world are two particles come in collision contact with one another and then outgoing particles. And the only restraint that we've really put ourselves under so far is the restraint in which the conservation of momentum is applied. And so what happens inside the black box is, again, somewhat of a black box. We don't know if conservation of momentum actually applies inside that box. And what renormalization coupling is going to do is going to put an upper limit on what exactly should go on inside that box. And so without further ado, make sure to hit that like and subscribe button, and let's get into the material. So we're going over renormalization coupling today. This is a very important topic, and it's going to be sort of the springboard into getting into understanding other types of physics as well. I mentioned in the last video that renormalization is a very important concept in statistical physics. It's also a very important concept in conformal field theories, which is also a playlist that I want to make. But with that being said, we have this renormalization coupling. What exactly is this? So before we start, let's recall that the original expression for our second order approximation was this guy right here. And so we can get rid of the q's, right? So the q's in the delta function go away, but we're still left with this guy right here. The reason we can get rid of the q's is because we have this minus makes it plus, and so those ultimately get canceled out. So we're left now with trying to understand this guy. And the reason, the way we got from here to here is we're saying, again, a conservation of momentum, right? K3 plus K4 has to equal K1 plus K2, right? These guys here are incoming, and these guys here are outgoing particles. And what the book does is it says, here's the integral. The mathematicians say it's this. Now, we're not going to go into this derivation. We're just going to say, okay, mathematicians, thank you for this answer. Let's proceed. So we have this answer. This here is our upper limit, right? This, forgot what that is in Greek, but this here is going to be is a number, and this here is our incoming particles, the sum of momenta for our incoming particles, and taking them squared. Okay, we can rewrite this, since this is the ln function, the natural log function, we can rewrite it like this. And when we do that, we have incoming particles, the ln of our incoming particles, minus the ln of our cutoff value. Right, so far, nothing's really changed. Let's continue now. We want to recall a few things. So recall, this is what we got for our first order approximations, what we got for our zeroth order approximation. This is what we got for our first, and this is what we got for our second. Okay? If we notice here that our zeroth order approximation is zeroth order in our coupling constant. Okay? And our first order is first order in our coupling constant as well. There's no exponent on the coupling constant. Then here we have our second order in our coupling constant. So when our Feynman diagram said that the order of the approximation depends on how many contact points there are, how many vertices there are. This is exactly how we quantify that. We say, what's the order? What exactly is the order on the coupling constant? And that tells us what the order approximation is that we're dealing with. Okay? And So let's think about this for a moment. If we only consider terms that contain some order of our coupling constant, that means we've effectively ruled out the situation in which the particles don't interact at all. Okay, so forget that. We want our first. We're gonna say, okay, the particles are indeed interacting. So if they're interacting, then that means the zeroth order approximation shouldn't be a thing, right? It shouldn't contribute to our scattering, right? Two particles can't scatter if they don't scatter, right? The scattering depends on at least one vertex going on. So we're going to renormalize this, and this isn't really, this wording of renormalizing isn't really the right word right now. I want to call this something else. So we're going to rewrite with respect to the coupling constant, because renormalization is going to come later. So what exactly... So we're going to say that this guy effectively is zero. When we say that there is scattering happening, that means this guy does not contribute. Okay? So here, we have... So we're going to say that this guy indeed, it looks like this, right? Because these are all the terms that are associated with the first order of the coupling constant. And then we have... all this here, right? So we want to take a look at this guy really quick, because if we are dealing with this equaling 0, right? This essentially is 1, right? But we can also think of this, or it's not 1, right? It's an infinite spike, right? If our momentum is conserved inside the black box. Right, so we're not inside the black box, but if our momentum is conserved before and after the black box. So we have this term here, so I just have this. So this whole thing actually looks like this, right? So this is 0. And recall that a delta function at 0, or this delta of 0, well, this is a spike at 0, right? This is a Fourier spike at 0. And so e to the 0th power is just 1, and we're redefining the integral to say that we're integrating over our space-time volume, okay, as the volume expands, it goes to infinity, right? So that's essentially the same thing as going from negative to infinity. We're just expanding the volume, okay? And then here, okay, we're taking the constant out, we're just integrating this guy now. When we integrate this guy, this is our space-time volume, right? And when I say space-time, that means this 3 here should actually be a 4. This is a minor detail, but I want to get this right. So space-time volume. Okay, so let's move on. So the new scattering amplitude is going to look something like this. So we're going to call it our scattering amplitude. This was our first order approximation. This is our second order approximation. We're going to redefine it. So this is redefined, right? So we have this tilde up here. This is different than the original scattering amplitude with all the terms in it, including the 0th order approximation. This is without the 0th order approximation. What we're going to do now is we're going to take 2 tildes, right? The book doesn't do it this way, because I think the book does it a little bit in a confusing way, so I'm going to try to do this in a little bit different way. The 2 tildes means we take this guy and we divide it by IV, right? So when we divide it by IV, we have this guy and this guy, and that effectively means that we can cancel out these guys here, this volume here, and this I here, and then this constant here just gets absorbed into this constant here. Okay. When I say constant is less than 0, I shouldn't have that. It just gets absorbed into the constant. Okay. So now what we have is a new scattering amplitude. This new scattering amplitude is a function of our coupling constant, or coupling constants, and our incoming particles. So S, we say here, is K1 plus K2. These are incoming particles. This is our cutoff value. And then we have further terms that are associated with 3 vertices, 4 vertices, and so on. But here we're just looking at 2 vertices in our Feynman diagram. So what are we going to do next? Well, this is where the renormalization coupling comes into play. We're going to say that our coupling constant is equal to our scattering amplitude plus a times the square of our scattering amplitude. And why exactly do we do this, right? So, well, we can only really make one observation, right? If we reduce this down to its simplest bare bones experimental case, what we're doing is we're saying that this guy here, this coupling constant, is equal to the scattering amplitude plus the scattering amplitude squared plus so on. Right, so effectively what this means is that when we calculate our coupling constant then enables us we can then approximate our coupling constant with scattering amplitudes, right? If you think of this as I take one measurement, that measurement is lambda. Okay, the measurement is lambda. Once I know lambda, then I can start approximating it, okay, with the scattering amplitudes, right? And that's this guy right here. And our scattering amplitude is a function of lambda itself. So that's what the renormalization is. We renormalize the coupling constant, right, to say that it is a function of scattering amplitudes, right? So you make one measurement, okay, and that measurement then should tell you everything you need to know, or that one measurement can be approximated, and those approximation terms are associated with higher order Feynman diagrams, or the number of the number of Feynman diagrams that you want to approximate with, right? So there you have one measurement, and you can approximate that measurement. Basically, the way you approximate that measurement is with your scattering amplitudes. Okay, so what we have is a rewritten scattering amplitude and a renormalized coupling constant. I just rewritten these guys right here. Okay, this we derived over here, and then this one we just said is what we're stipulating, right? We're saying that the measurement can be approximated by the scattering amplitudes. So what does all this mean? Well, when we look at this, right, we want to know what A is. Right, so A is important. That's a constant. Let's see if we can calculate exactly what A is. So what is A for an initial set of momenta S naught? Right, so S naught, so we should have S naught here. And so we approximate all this, right? So we're just plugging everything in, right? Lambda is a function of our scattering amplitudes. Again, a function of our scattering amplitudes, but we have to square this one, right? So I should be a little clear here. This guy here is lambda, and then we square it right here. Okay, so then so here is this guy, here is this guy, this guy times this guy squared again. We have to square him, and then we multiply him by this, which is right here. You need to fix that, ln. And then we have higher order terms, because once we use this guy, well, that's going to be a to the fourth power, and we're just going to ignore that for right now. So we're approximating again. So this actually has to be an approximation. So these are approximations. So this guy, so we have this guy minus, so this guy's here and this guy's right here. Right, so a naught. And so we get this and this. Okay, well, this just means that a is equal to this guy right here. So a is this guy, because a property of the logarithm is that we can, if we inverse the argument, then we can get rid of the negative sign. Okay, so this is important. So let's box this guy actually. Put a little star there. So that's important. The renormalized coupling constant, again, so we said was this. So if we plug A, we know what A is now. We plug it in. All right, so this is now our formula for the renormalized coupling constant. All right, so again, what we're saying is that the coupling constant that you measure can be approximated by our scattering amplitudes. Right, so that is this formula here. So we want to know now. Here's the question: for an arbitrary initial condition, right? So the initial condition being K1 plus K2. Those are the two incoming momentum. We want to know what exactly this renormalized coupling would look like for a general S, for a general set of initial conditions. So this isn't too hard. What we do is we say, okay, this is what we said before, right? This, and we're plugging things in now, right? It's the only difference here is that the argument here is S, not S naught, right? So we plug lambda, which we got, into lambda here, right? So we plug it here, plug it into here, and we have this term out here. All right, same term out here. So now, this is okay. So we have everything here drops down minus. So we have a squared. Let's see here. This should actually be squared, right? Because a squared multiplied by this guy, right? And then we have higher order terms. All right, so we now say that, let's see here, this should be not, so we drop this guy down here, and these two guys are the same, right? So we can say that we combine these two guys, right? So if these two guys are the same, with the exception of a sign here, it looks like the sign, we flipped the sign, right? So we flipped the sign because we went to, let's see here, squared S, these two guys, S naught, ln of S, S naught. Oh, they're not the same, right? So they're the same in this term, right? So we're foiling things out, right? So when we foil things out, we see that the thing that's similar between the two is this guy. Okay. And so when we go from here to here, right? So we foiled him out, and we have we can also FOIL our C out. Okay, what's left is this guy here, this guy here, and this guy here. And by the property of logarithms, where when we add or subtract them, so what's going on here is we have, so I realized that we should have had a plus right here, right? So when we have that plus, then we're using the property of the natural logarithm, that ln of AB equals the ln of A plus the ln of B, right? So that, again, is a property of the natural logarithm, and that's what allows us to go from here to here. And then what we're saying here, so we have this term here, and so another property of the natural logarithm, again, is that we have log of this and log of this, so we can combine those two, and we could see here that the cutoff goes away, right? So we can actually get rid of that cutoff, and what we see now is that our scattering amplitude is now a function. Our scattering amplitude here is now a function of just the initial set of momentum, okay, which we have here and in these two terms, right? So what we've done. Well, let's go back for a second. Let's go back. What we've done is we've said, okay, we stipulated that we have a renormalized coupling constant, that we've said that this is in terms of our scattering amplitudes. And when we did that, when we made this claim, right, it's a fairly intuitive claim to say, right? What you're saying again is that we make one measurement out of this process. Okay, and that one measurement we can then approximate. We say, okay, the first order approximation of this term is going to be associated with one vertex. Okay, if we add another term to try to approximate, then we're going to associate that with two vertices being contributed, and so forth. And so, again, it's not a wild thing to claim. And so we got rid of the cutoff by doing that. When we made that claim, we went through all this mathematics, right? It's just manipulation to get this right here, where we said, okay, now there's no more cutoff. So let's recap for a second, because this is pretty important. So we made this claim here, right? This is our claim that we made. We made, here, I'll erase this. We made this claim where we have our scattering amplitudes and we also had this problem again where we had this cutoff. This cutoff could have been arbitrary. We don't really know what this cutoff is, and our goal is to get rid of the cutoff here. And by making this claim, the cutoff went away. Right, so the cutoff goes away. And this is what so renormalization ION leads to this renormalization leads to doing away with the cutoff, right? So I'll just that's our cutoff is gone. That's essentially what we've done here. And this is going to be very, very important, because when we take a look at this equation, our cutoff essentially is our initial, it's not really a cutoff, but our limiting factor here is going to be our initial condition, right? So what we've turned this into is a problem where we say, okay, we just want some initial conditions, and then let's see what happens, right? We can very easily graph something that says, what we can ask the question, what exactly happens to what exactly happens when our initial condition increases, right? What exactly happens when the two incoming particles have momentum such that they're so huge to the point where they might be going near the speed of light. So suppose we had two particles going at near the speed of light. That means the denominator here is really big, and if that's really big, then the argument inside the ln is going to be really small. Right? So if the argument inside the ln is really small, if we recall the ln function, it looked the smaller you get on S naught. If we recall the ln function, looked something like this. When the S, if this was S naught, then suppose this is really big, right? So suppose this is like 2.9 times 10 to the 8 meters per second or something like that. Or this is like a really, really big momentum, right? Very large. I'll just write very large, right? So our value looks something, or that's actually not our value, right? Because the argument is very small, right? So if S naught is really big, this, what we're actually graphing here is S over S naught. So if S naught is really large, then we're actually somewhere in this range, right? So we're gonna get a value somewhere down here, right? So this is going to be negative, right? This is going to be a very, very small value. And if that's very small, then if we go back to our equation, this term here gets really small, and we can essentially approximate with our initial condition, right? So with our initial condition, without any of these terms, any of the preceding terms. So that is renormalization coupling. So I don't want to ramble on for too long here because this video is pretty long, but we are going to cover this again in some later videos, and we're going to see a little bit more what this can tell us. So, but in the next coming videos, we're going to look into elementary models. This is going to be an introduction into chapter 12 of the book. So with that being said, I hope you guys have a nice one, and I'll see you guys in the next video.